Welcome to Aerial Services Ortho and LiDAR Accuracy Concepts, the final of 3 webinars in the Aerial Services 2013 Summer Webinar Series. This is your host, Joshua McNary, Director of Corporate Development at Aerial Services. We are pleased you have joined us and hope you walk away having learned more about ortho and LiDAR accuracy for your geospatial applications. But first, a few housekeeping notes. 1. You may ask questions via the questions pane on your screen. We'll collect these questions for responses from the speaker at the end of the presentation. 2. We want your feedback. Contact us via the questions pane or via the post-webinar survey with any ideas, suggestions, or concerns regarding the webinar. 3. The post-webinar survey will appear on your screen after you leave the session. Please use that as an opportunity to share your feedback. 4. Lastly, but not least, note that Aerial Services will have another webinar series this fall. We are not ready to make an announcement on the topics yet, but look for more information soon regarding our fall webinar series. Keep an eye on www.aerialservicesinc.com/webinars for more information and to register. I am now pleased to introduce my colleague and friend, Aerial Services President and CEO, Mike Tully, who will share his expert knowledge with you today. Serving as President and CEO of Aerial Services, Mike's duties include managing company endeavors, supervising GIS programming, and overseeing the information technology and technical resources of the company. Mike has managed the company as co-owner since 2000 and was named President and CEO in 2003. He is also a certified photogrammetrist and a certified Geographic Information Systems professional, as well as an active member of the Management Association for Private Photogrammetric Surveyors, MAPS, where he sits on the board of directors. So with that, I'm happy to turn the session over to Mike, who will get on with the show. Mike, the floor is yours.
Hi, everybody. Thanks again for attending today. And I'd like to just get started and talk about accuracy concepts and as they relate to ortho photography and LiDAR. As professionals, we need to know what we're doing, quite frankly. Orthos and LiDAR data and services represent incredibly complex geospatial data sets. They're difficult to measure well. They're incredibly useful and are very prevalent in all. But did you know that they're all inaccurate? They're full of error. Today I'd like to talk about several aspects of accuracy by highlighting some of the common problems we see with data and how stakeholders use it. It's unfortunate that even today, with many excellent, well-defined methods of ensuring accuracy, that there's still a lot of data delivered by professionals that fail one or more essential tests of accuracy. So we'll go over all these concepts today. You know, we've all seen this kind of stuff before, bad data. Sometimes it's the underlying data, like a DEM that's bad here or here. Sometimes other data sets, in this case vectors, don't line up well with our base mapping. So what do we do when this happens? Are my road center lines bad, or are the orthos bad, or are they both bad? And how do you know? And where do you go to find out where the problem lies? So today we're going to cover these 4 things, basic concepts about error, how we quantify error associated with geospatial data sets, and then how to report that error so that it's understandable and comparable between data sets and users, and then some thoughts on how to procure geospatial data with some amount of specified accuracy. So first we'll get started with the basic concepts about error. I said earlier that all of our measurements are made with error. Everything we have, all of our base mapping is wrong, basically. There's error associated with every pixel and with every LiDAR point. There's error associated with that. It's not the perfect measurement. It doesn't represent the perfect latitude, longitude position on the face of the earth. There's no way around that. Nobody can measure anything perfectly. It's a limitation of our instrumentation and our procedures. But knowing this, what can we do? And basically, we need to quantify and report this error. We need to understand the error, how to quantify it, and how to report it. When talking about accuracy, it is important to understand these terms, precision and accuracy. We need to understand the error associated with our data and whether it's imprecise or inaccurate. And as this graphic illustrates, you can see that accurate and precise data is what we're after. Precision of a data set describes the closeness of one measurement to another. This is affected by random errors. So the more random errors you have, the less precise, the less grouped together our measurements of a particular point are going to be. Accuracy, on the other hand, describes the degree of perfection obtained in a measurement. That is, how close to the true value the measurement really is. And accuracy is affected not only by random errors, but also by systemic errors, like bad calibration or some equipment issue. So in the absence of systematic errors and blunders, precision and accuracy would be equal. So it's important to understand these terms, and we'll talk more about these here as we go along. So just some basic truths about error, some more basic concepts. One is, now that we know that error is certain, and no matter what we're measuring, whether it's a pixel or a LiDAR point or a surveyed location on the ground, knowing that error is certain about that measurement, the first thing you need to admit is you need to care about accuracy. Because we know there's error, you better be aware of it, and you better be concerned to quantify and understand that error. We've got to not only quantify it, but describe it. We've got to know how to describe it. We've got to know how to report that error. All these boil down to this thing, which is fundamental, that if you don't understand, if you as a professional geospatial person, if you don't understand the nature and quantity of error in your base mapping, your use of that data is unprofessional and irresponsible. So understand these things, and hopefully this presentation will help all of our understanding. Associated with this is the idea that accuracy costs money. The more accuracy that you want, the more it's going to cost generally. And so we need to know how much accuracy is needed, because we don't want to waste money on over-accurate data. And likewise, we don't want to try to pinch pennies and end up with data that doesn't meet the needs of the stakeholders of the data set. So once you understand the accuracy you can begin to define how the data is going to be used, and more importantly, what it should not be used for. We call this intended use. A professional is very concerned, or should be very concerned, about the intended use of the geospatial data set because of the threat to public welfare and safety if it's used inappropriately. And likewise, because it's related to accuracy, you need to match that the needed accuracy with how the data set is going to be used to maximize the value of that data set. For example, Tiger data. If you were using Tiger data, which has a horizontal accuracy of 25 feet to align your property boundaries to, may not be a good idea if your ortho accuracies are in the range of 12 inches. In fact, the metadata for Tiger about accuracy says, quote, "No warranty, expressed or implied, is made with regard to the accuracy of the data in the Tiger shapefiles, and no liability is assumed as to the positional or attribute accuracy of the data." So we expect it to be 25 feet off, but there's no guarantee that it is, and you use it at your own caution. Do you know that when you're using the data? It's perfectly okay to use tighter data. It's not okay to use tighter data and not understand its accuracy fundamentals. Google Earth is another good example. What's the positional accuracy of Google Earth? In fact, there's no accuracy defined with Google Earth data according to their Wikipedia page. So different geospatial data sets are created for different reasons, and they can be responsibly used for some purposes, but not all. And it comes down to understanding the accuracy and quantifying that so you know how to use the data responsibly. Which brings us up to accuracy standards. They're important. These are standards, conventions used to quantify and report accuracy. We're going to talk about them more in a few minutes, but it's important to understand that they exist and that they're important to use not only when we're procuring geospatial data, but when we're downloading or using somebody else's geospatial data. Accuracy standards are important because they help us facilitate comparing data sets with one another. Because they're a standardized way of reporting and quantifying error, you can take the accuracy statement from one data set and compare it to the statement of another data set and determine intelligently and objectively whether or not those two data sets will meet the intended use that I have for my geospatial project. Accuracy standards are always changing. It's important that you keep up with them. Over time, our orthos continue to increase in resolution. You know, we used to think 1 meter orthos were great. Now a lot of municipalities and others are routinely collecting 3-inch orthos. LiDAR is the same thing. As our LiDAR sensors become more and more sophisticated, the point density becomes higher and higher, and we're able to measure things more and more accurately. So accuracy standards evolve as our technologies evolve, and they'll change, and they are changing even today. So it's important to know them and to keep up with them. And one of the reasons I mention that is because we see people using old accuracy standards all the time when procuring geospatial data, and it's just inappropriate and dumb to do so. And we'll talk about that more later. So before we can really get into accuracy, we do kind of have to talk about what we mean by accuracy. It means different things to different stakeholders. Accuracy in the general sense, or in this sense, means do measurements made in the data and those made in the real world differ? How close to the truth are our measurements? Precision we talked about. What's the exactness of our measurements? Or maybe somebody's thinking that accuracy just means it's complete. Are all the information components comprehensive? Some people think of accuracy in terms of currency. How old is it? Does it reflect what's on the ground today, or is it 6 months or 12 months old? Consistency. Does the information agree with each other? Were the different features compiled consistently across the data set? Lineage. How is the pipeline moved through the production process? There's a variety of other things like credibility or subjectivity or interrelatedness. But understanding what's important to the different stakeholders and how they perceive accuracy, all is very important to include in any specifications you might need for procuring a data set. So quantifying error is the next thing we want to go over. And some of you are more familiar with how this is done, but for those of you that may not understand how we actually quantify, how we measure how much air is in an orthophoto or a LiDAR data set, I'm going to share some of these fundamentals. And this graphic here basically shows us an ortho photo. And we can see this red point, which is the location of a ground control point, the intersection of two sidewalks. That appears in the ortho photo we've just produced. And then the green target there, upper left, is where the actual surveyed location exists within our ortho. And you can see there's a difference there. If the ortho was made without air, the red and the green targets would be coincident with the corner of the sidewalk there. But they aren't. There's air. So we measure that. We want to measure the difference in how far offset in X and in Y those two observations are, and then calculate that radial air, which is basically just the hypotenuse of that right triangle. And that gives us an objective, quantifiable measurement of how far off our surveyed or the true coordinate is from the image coordinate, or what we've measured in our orthophoto. I'm using an ortho here. We could just as easily, the same process is used with LiDAR data. You're still measuring the difference in offset between the true value, the surveyed location, and the observed value in your LiDAR or your ortho data set. So what we're talking about here is applied equally well to orthos and LiDAR data. Okay. Usually, to test a data set, you need at least 20 points, 20 ground control points to spread throughout the area to statistically quantify how much and the type of air that exists. So, assuming we've got 20 points or so, if we were to measure that air, that radial air, as we just saw in the previous graphic, and then plot those on a chart, we'd get a distribution something like this. Those black triangles are the observed air for each of those points, and you can see we've got a mean of about 0.15 units. And some of that air is to the right, which is higher. It's off 0.2, 0.3, 0.4 units off, and some air is less than the mean, and that's typical. If we were then to count the frequency of those airs, you'd see those bar charts behind, where you've got a lot more air that's in the 0 range and in the 0.3 range than near the mean. And as you get further out from the mean, the frequency of those air observations decreases. That's pretty typical in actual geospatial data. What we see typically is we see a distribution of air in our data sets that approaches what's called normal. And all that means is that the distribution is more or less shaped like this curve is. And what's nice about that, and what's really important about that, is that if the air is distributed according to this normal distribution, we can make a variety of assumptions about that air and about further observations of our data set that are very useful. For example, we know that if we know by measuring the area underneath that curve, what the probability of finding a measurement would be. So in this case, we go out 2 standard deviations, which happens to be 95% of the area of that curve. We'll see here in our data set that all those observations are contained within that area of the curve out to 2 standard deviations, 95% of the area, except for one observation. So that's interesting, right? 95% of all our observations fall within this area of the curve. Another way to express that in English would be that we're confident that 95% of the measured control points will have an error of plus or minus 0.7 feet, which is what we saw on the graph there from the actual surveyed location. And because we are assuming normality, I'm going to go back to that, because we're assuming this normal distribution, we can say statistically that if we were to go out and measure a 21st control point, that we're 95% certain that the error associated with that value will fall somewhere between minus 0.55 feet and plus 0.85 feet, somewhere inside that shaded area. And that's what this theory of this assumption of normality does for us. It tells us how much confidence we have that observations will fall within that range of values. And this dovetails very well into the accuracy standards. And the prevalent standard in use today is the NSDA, the National Standard for Spatial Data Accuracy. This is the standard that expresses error associated with geospatial data sets using an error amount and a degree of confidence, a percent of confidence. Just like that, a 0.7 feet with a 95% confidence, or whatever confidence you want. NSDA doesn't dictate what those values should be, but it tells you how to state them and report them so that they're comparable between data sets. We'll talk more about the NSSDA here in a bit. There are other accuracy standards. ASPRS 1990 standards for large-scale maps are still out there. They're still used. National Map Accuracy standards are used. Those two standards today should not be used. ASPRS 1990 standards and the National Map Accuracy standards, they're irrelevant. They're based on old methods of mapping, basically tied to paper maps, and they are not appropriate. If you're soliciting or trying to understand error associated with a data set, you want to use the NSSDA standards. There are other standards that are important, like FEMA and USGS, and you need to understand what those standards are if you're delivering data or using data from those organizations, because they've defined their own standards. But what's nice about them is they're both phrased and coined in NSSDA language. So the point here is, don't use these older standards, ASPRS and National Map Accuracy standards. Understand NSDA and know if other standards for a particular organization's data are relevant to your use or not. ASPRS is also developing new standards now. These are a picture of some of the draft accuracy standards for digital geospatial data as of 2012. I don't believe they've published these as final yet, but this is kind of what they look like. And these were developed because technology is changing, as we've talked about. They are based, the old ASPRS standards were based on Class 1, Class 2, and Class 3, where Class 1 is a base level. Class 2 is just twice as bad as Class 1, and Class 3 would be 3 times as bad as Class 1. So very simple to understand. These new standards have developed this X, A, and B standard also, where X is a new high accuracy level for the most demanding engineering applications. These are the accuracy requirements for the X level. And then there's the A, which is standard accuracy, and a B, which is less accurate. So these are important new standards and some that we should all be familiar with. Solicitations today should be made using either NSSDA or perhaps these new ASPRS standards. What's important to notice here is that like the NSSDA, these ASPRS standards are specifying this RMSE, or the amount of error, in this case 12.5 units, and an associated confidence with that measure. Okay, well, when we report error, we're going to pick some standard, hopefully the NSSDA. And there's basically two ways to report the quantity of error that we've discovered in our data set. And then we can use the word tested, saying this data has been tested to meet this accuracy level. And this is the best. This is the most certain statement we can make about a data set, is that it's been tested to meet these standards. The next best thing, which is acceptable but is not as rigorous, is a statement that says this data has been compiled to meet this standard, which means we haven't gone out in the field and tested the data, so we don't really know for certain that it meets these accuracy standards, but professionals compiled it according to known methods that, when used appropriately, will create data that meets these standards. Secondly, it's important that this accuracy statement is included in the metadata associated with the geospatial data set. This helps anybody that happens upon this data later, your stakeholders or the public or anybody else, to be able to understand just how it was created, for what use, and just how accurate it is. Whenever you're trying to validate, verify accuracy of a geospatial data set, it's always best to use a third party. You don't want to do it yourself if you're the procuring person. You don't necessarily want the person producing the data. It's best to get a third party, independent of the user or the producer, to go out in the field, measure those control points, and perform an accuracy verification. That's not essential. It's the most pricey option, but generally you will get the best results and the best certainty of accuracy of the data set using a third party. Okay, I want to change a little bit here and talk about the types of error that are important to quantify in orthos and LiDARs. Orthos are far simpler or less complex than LiDAR, and so accuracy is a little easier to define and quantify with orthos than with LiDAR, as we'll see here in a minute. But of course, positional accuracy is very important in orthos, making those measurements on the photos between our observed and measured ground control give us positional accuracy. The NSSDA statement defines the positional accuracy. But also important is radiometry. How does it look? Are the colors consistent from one side of the orthophoto mosaic to the next? Smears, are there smears? Are there voids, areas where there are no pixels? And are there other issues, clouds or standing water or anything else? You'll have different specifications for acquisition of those orthos that you'll come to bear here. Our tool of choice in defining and reporting the quality of an orthophoto data set is an application from Spatial Information Systems called Accuracy Analyst, which is used for orthos, and Topo Analyst, which is used for LiDAR quantification. The reason for that is our shots like this. It allows the producer or the end user to very easily and quickly run the data set through descriptive, consistent testing methods that are very robust, and then provide reports that are very complete and include informative graphics like those shown here that show photos of the ground control point from an oblique angle, like in the top left, and where the observed and measured locations existed, as the graphic below says. In addition to that, it shows all kinds of information about the data set, some of which you can see in that lower graphic there, as far as how much air was around each point. Was the air off to the north or to the northwest? Was it lots of air from the mean, or was it really tight? All of those statistics are displayed for all of the points in a very consistent, clear manner using this type of commercial software. LiDAR is a different animal. It's a far more complex data set. There have been there have been no commercial tools to quantify all the different aspects of air associated with a LiDAR data set until Spatial Information Systems Topo Analyst came to market several years ago. And again, this is what we use to quantify air and LiDAR. Until Topo Analyst came out, and still today, probably the most common method of quantifying air and LiDAR is just simply looking at it. That's not the most objective way to quantify air in a LiDAR data set. We don't do that with orthos. We measure things in orthos. We measure how much offset a point is. And we need to do the same thing in LiDAR, and it frankly wasn't possible to do easily until Topo Analyst came around. And we love it because it does provide that robust testing procedures that go well beyond simple visual testing, as we'll see here in a second. For example, not only do you want to know how accurate a point is in LiDAR, but this graphic shows several strips of LiDAR as different colors. And it's how we need to know that those strips overlap each other and that the overlap meets our specified amount of overlap. So it provides these types of graphics to show that the coverage between each strip does have the necessary overlap. And if there were gaps in overlap, they would show up very clearly in a graphic like this. Likewise, the center one shows us a more detailed inspection of the overlap area. You can see there's some intrusions in overlap down there where the sensor misfired, or some other reason that caused that perturbation there. And that may be important, it may not be important, but at least you see it and you can deal with it intelligently. The Topo Analyst also gives you a great graphics of voids or holes, and as most of us know, pavement and water are notorious for producing holes in our LiDAR data set. Well, when you have a graphic like this that shows you all the voids, you can begin to see that some voids are acceptable. They're water, they're streams, or lakes that you can see here. But you can also point out easily see voids that are not acceptable and need to be looked at and studied and understood, quantified. Point density. Many specifications for LiDAR require a certain point density, and TopoAnalyst very quickly gives you a graphic showing you point density, and if there's issues somewhere along one strip for some reason, you had low point density, it would show up here, or if there's holes or whatever. You can see it here very graphically. Water voids, same kind of thing below. Not only can you see voids, but you can see how they relate to point density also. Some of the reports that we get using these tools that I think are very important for the end user, for the stakeholders, are reports that summarize the metadata very nicely. And again, what's nice about using a commercial off-the-shelf package like this is that every data set will have the same reports formatted the same way, so that you become very comfortable and it gets very easy to read and interpret as you move from one data set to another. So it has a metadata report. It has a complete report on control point errors, showing you graphically where the control points are at and what kind of errors associated with each one, the total RMSE or the total variance with the data set. If you've got LiDAR and classified in different classifications, it will perform the statistical analyses within each classification to show you how much error is in each class of LiDAR points. And then it shows the distribution of point errors. Again, very important to understand not only the amount of error, but how they're distributed across from the mean. For each adjacent LiDAR swath pair, an overlap can be computed. It's subdivided into a number of segments, and then Z's, the LiDAR points within each of these little blocks, within each of those overlaps, are measured between the two overlapping strips, and you get a statistic that measures the relative accuracy of strip 1 with strip 2, and strip 2 with strip 3, etc. This you can't do visually. You have to be able to use this objective measurement tool bundled with this software to estimate relative accuracy. And you get a graphic picture of that, which is very helpful. It produces this thing called Z-diff rasters, which again helps you to just visualize how great a difference there is along the overlap between two strips, to help you visually see issues with the data set and then develop a strategy to deal with those issues. It's just as easy with this type of software to combine orthos and LiDAR and produce a variety of reports and tests and statistics that measure the fit between different data sets, that they register, co-register with each other well. When procuring geospatial data sets, it's important to, again, understand what you need and what the relative costs are. And this graphic just basically shows you what to expect. The more accuracy, the more money. As far as orthos go, land use is your least demanding ortho photo, and it doesn't cost very much. Your accuracies aren't going to be great. You don't care that they're great. You don't need to measure the height of a curve with orthos intended to use for land use planning. Whereas for engineering purposes, they're going to cost much more money because you do need to measure the height of the curve and things like that. And accuracy is much more important, and it's going to cost you more. LiDAR, the same thing. Force inventory, accuracy is not a real important. Whereas if you're measuring the number of cracks and holes in pavement, you need much more accurate data, down to millimeters perhaps, and it's going to cost more money because of that. So making measurements is difficult, and as to increase accuracy has an effect on a number of other variables like flight altitude, flight speed, GSD, points per square meter, things like this. So as you adjust those variables, your price increases to get more demanding accuracy. So I said earlier, we don't want to use national map accuracy standards. We don't want to use the old ASPRS standards. When procuring geospatial products, use NSSDA language or some of the draft ASPRS standards. Forget about using the old ones, and I can't emphasize that enough because we still see solicitations. It is more common to see solicitations using these older standards, which are just inappropriate for today's digital data, than for the correct NSSDA standards. Another thing I might add is don't dictate to the provider how data should be created or collected. Let them figure out how to do that to meet the specifications that you have. You define the deliverables. What kind of GSD? Tell me how accurate it needs to be. Tell me if it needs to be unobstructed view of the ground, things like that. And let me, the professional, decide what sensor to use, how high to fly, how fast to fly, things like that. Let me figure that out, and you dictate the specifications that it needs to meet. Avoid vague specifications. We see this far too commonly, like this example here. Spot elevations will be shown to provide complete and accurate vertical information. Well, that's great, except every firm responding to a statement like this will likely define complete and accurate in disparate ways, which will make it impossible for you to compare prices and scope between different proposals you receive with a solicitation like that. So complete and accurate is not objective and means different things to different people. It's vague. Don't use language like that. Another example is, we see this a lot, the 100 scale digital orthos shall be compiled to meet 2-foot horizontal accuracy at 95% confidence level. This is getting better because they're trying to express accuracy requirement using NSSDA pros. But what is a 100 scale digital ortho? There's no such thing, really. Digital orthos, because it's digital data, are all scales. We can zoom in and zoom out. And so scale, including a scale with digital orthos, doesn't make any sense. So don't reference scale with digital orthos. All you need to say is the accuracy requirement, 2 feet, horizontal accuracy is 95% confidence or 90% confidence. It's okay to use 80% confidence. It's your data. You can specify whatever accuracy you want or use somebody else's accuracy specifications like USGS or FEMA, etc. Okay, so in summary, assessing accuracy of geospatial data is not easy. It requires informed, diligent professionals that understand the data, acquisition and production methods. It requires users to understand these principles and methods available to help them either ascertain accuracy or to understand how to interpret reports given to them by the provider or their third-party QA contractor. Internal accuracy production checks. All companies have their own collection of accuracy and quality tests. Some use commercial off-the-shelf software like SIS. Others have just invented their own tools. There is great advantage to using commercial off-the-shelf alternatives so that these tests are standardized, the reports are standard, and it's easy to repeat the exact same test across every single data set. There's a complex combination of tools and methods needed to assess accuracy. There's no single tool or easy button for all the diverse geospatial projects that we encounter. Most companies have several tools to assess just how do I know it's good, and some work better than others. There's a variety of industry working groups that have created standards that are very important for all of us to use and understand, from ASPRS and USGS to FEMA and the Corps of Engineers. They all have standards that help us answer the question, how good is it? And then, again, commercial off-the-shelf solutions are available, and I encourage all of us to use them, both producers and users. These tools are very useful for both groups. So many geospatial data providers and users are using these tools and techniques to help us assess accuracy of our DEMS and our orthos and our LiDAR data. And more accuracy and better accuracy verification is needed to ensure the information delivered and consumed by this profession will meet the needs of our end users and protect the public from bad data. Just for your information, I've included here some of the primary sources for information about accuracy for LiDAR and ortho geospatial data sets, and they're here, and we'll make all these slides available on our website here in the next few hours. And with that, I'm happy to answer any questions that any of you might have. Josh, I do not hear you.
Mike, here I am. Thank you for the presentation today. Appreciate the very informative and useful presentation. I think we learned a lot about accuracy concepts today, so appreciate your time. Now, as we get into questions, I wanted to make a couple notes before we do so. We do not want to get overly project-specific during the Q&A, so if you ask any project-specific questions, we'll reference those after the session directly with you. Second, you can feel free to call us anytime to discuss any remote sensing issue. If you think of something after the session is over, even if it's a general question, we're more than happy to help. Okay, Mike, so we've got a number of questions that came in. So I'm going to just take them from the top, and we'll try to hit as many as we can, all right?
Okay.
Okay, so there at the final slide, you talked a little bit about where they can find some documentation on current accuracy standards. But outside of our slides and some of those notes that you made there, are there any other good online sources for accuracy standard information?
Sure. The ASPRS.org will have standards there. USGS, there's a couple places at the USGS site. They're the NDEF site at the USGS domain. Both of those places will have good information. There's also a brochure, a PDF out there from the state of Minnesota on how to measure accuracy in an ortho project. It's very good, very written for laymen. And I don't have a direct reference for that at the top of my head, but do a Google search for Minnesota ortho accuracy, and you probably find it.
Great. Okay. Well, we had a number of people, Mike, that asked about any kind of relationship between whether in orthos GSD and for LiDAR point densities, essentially higher accuracy data or higher, I'm sorry, you have to correct me, Mike, giving the right terminology, but higher density data, essentially, and how that relates to how accurate it is. I know you touched on this during the talk, but can you clarify that for people, that the idea of high resolution ortho imagery or high density LiDAR data and how it is or is not accurate?
Sure. Now, it's of the common misunderstanding that higher density orthos or higher density LiDAR means more accurate. That generally is true, but it is not necessarily true. Just because my pixels are really small and I have a really small GSD, meaning high resolution ortho, or just because I have 500 LiDAR points per square meter doesn't necessarily mean it's more accurate than something less dense. So you have to understand what the accuracy for a given data set is. And the only way to know that is to find that if it was tested and if it was reported using these standard accuracy guidelines that we've talked about. So don't make the assumption that a 3-inch ortho is more accurate than a 12-inch ortho. It's not necessarily true, and there's no relationship between density and accuracy. Accuracy is defined by lots of other things than simply the density of the points.
All right. Next question, Mike, is what's your perspective or Aerial Services perspective on having surveyed checkpoints included in a solution versus not? I mean, with many of the technologies today, we can fly theoretically without those checkpoints on the ground and still get a reasonable product for certain applications. So, can you speak to that issue?
I guess two thoughts come to mind when you ask that. One is to not have checkpoints or control points to verify the data collected. You either need to have trust in the data provider that they're professional, they're skilled, and they'll deliver according to spec, whether it's tested or not. Or you need to have fairly loose accuracy expectations, or at least you don't expect to have a high level of confidence that the data will meet a particular accuracy standard. So it is always best to have control points so that you can objectively measure the accuracy of a data set. That's always best so that you don't have to guess, so that your confidence is high. You might have very high confidence that the accuracy is very low, but that's still good, right? That's what you paid for. You paid for low accuracy, but doggone it, you want to know that it meets that low accuracy standard. That's far better than having data where you have no confidence how accurate it might be. So using control is always better. It's always the best practice. But you don't necessarily have to have it if you got a good data provider, and you don't need, the highest levels of confidence about the data.
Okay, Mike, there was a series of questions that came in referencing the 20 ground checkpoints that you mentioned during your talk, and how that relates to the standards you were talking about, and if that was an example of what you might consider for a project for a given area, or if that was a part of the standard. Can you speak to that and what you were referencing there?
Yeah, sure. Yeah, that's just the minimal number of points needed to statistically define or describe the accuracy of a data set. So that's just a bare minimum. So,
and Mike, that's a bare minimum for what? For what area? What is that? Does that have any relevance on the actual size of the area that you're testing, or is that for a given portion of it?
Yeah. Well, so not directly. It doesn't necessarily relate to the size of the area. It can be 20 points across a large area. That's sufficient to make a statistically valid statement about accuracy for that data set of any size.
But more practically, in the real world, we're going to look at that much more carefully because everything on Earth isn't uniform. So if you've got a large area that's covered by orthos or LiDAR, for example, you're going to have areas that are void of things obscuring the ground, and you'll have areas that are, thickly forested or covered with crops. And so you're going to want to design the projects with control points, maybe 20 control points in different areas, so that you have a better estimate of error associated with these different areas of content, whether it's urban content or farmland content or forest content. Same way with LiDAR. In LiDAR, we're often classifying these billions of points into 6 or 7 or a dozen different classifications, from bare earth to buildings to vegetation to things like that. So again, we're going to want to put a minimum of 20 points in each of those types of classifications. So 20 points scattered around your bare areas, 20 points in your forested areas, 20 points throughout your urban areas, et cetera, et cetera. So again, 20 is all you need to say something statistically, but in practice we're often using more than that because the conditions on the ground vary from one side of the project to the other. And you really do need, a professional, somebody that understands the sensing technology and the photogrammetry to design a project so that it does have sufficient control so that you can make confident statements about accuracy.
Okay, thanks, Mike. Continuing on, we got a number of other questions. We're almost up to our 1 hour time, but we're going to just keep going and try to get through the rest of these questions. So for LiDAR, you showed those strips of image of reports with the strips of our flight paths. How, for LiDAR, and for that matter, Ortho, how is it affected with the pitch, roll, and yaw of the airplane, and how could that potentially affect accuracy for a given project?
Well, as I think I understand the question. So as a aircraft is flying over the Earth, if it pitches to the right or to the left, then those LiDAR points are going to pitch to the right or to the left with the aircraft. And so the strip on the ground, the area covered on the ground, is going to pitch to the right or to the left, which can create a bulge on one side of the line or a hole on the other side of the line. So yes, pitch, roll, and yaw all have an effect on where those points fall on the Earth and whether or not there's going to be resultant holes or no overlap between strips on the ground. And this goes for LiDAR and for Ortho.
Okay.
So typically we know how much tip, tilt, and yaw is acceptable to avoid these kinds of anomalies. And so usually specifications include parameters that say you won't have any more tip, tilt, or yaw than this amount. And every time information is sensed, we record those 3 variables so that you have, or we have, the provider should be able to provide to the end user a report that shows every time we sensed, here's what those values were, and we can verify that tip, tilt, and yaw were met the specifications and demonstrate that there are no holes between strips.
Okay, Mike, how about for LiDAR, how is the classification error determined? I believe you referenced that in one of the reports you showed.
I don't know what you mean by classification error. If by that you mean how do you quantify the error in one classification over the other, then that's easier. Basically, you've got at least 20 control points in classification type A, and you've got 20 other control points in classification B, and you're going to just go measure the LiDAR points that strike those 20 control points in each of those two classifications, and you're going to measure the error associated with those LiDAR points and the control point, and develop that statistical report and an accuracy statement for each of those different classifications. With LiDAR, you usually have a thing called fundamental error, and I just forgot the component error. But the fundamental error is basically the overall accuracy of all the classifications combined, whereas the different component errors is a accuracy for each of the classifications within the LiDAR data set.
All right. So Mike, how do we come up with a means to calculate the horizontal error in LiDAR? How does that work?
The same way that we would do it with orthos, and that we've got a target on the ground that's been surveyed, and we know the X, the Y, and the Z position of that target. And we take the LiDAR point, and associated with every single of the billions of LiDAR points is not only a Z, but also an X and a Y coordinate. And so we can, if there are 5 LiDAR points that strike our target, we can calculate, an average X, Y, and Z of those 5 points and compare that to the actual measured, controlled position of that target, and come up with an accuracy statement for horizontal and a separate accuracy statement for vertical.
All right, Mike, we just had someone that asked if you could clarify what RMSE is, what that means, and perhaps give us a quick lesson on how it applies or how it's useful for these accuracy analyses.
Yeah, you bet. I try to avoid using too many statistical terms, but RMSE means root mean square error, and it's basically just a measure of variance. It measures what the distribution of that error looks like. Is it really tight around the mean, so the error doesn't vary much beyond the mean of this data set, or does it vary a great distance from the mean, which means our error values are really high, they're really low, and they're all over the place. So a small RMSE would mean that data is very tight around the mean, whereas a large RMSE means that data is very loose around the mean. So it's just a measure of variance, and RMSE is one of the key factors, one of the key statistics used in NSDA and these new ASPRS accuracy guidelines that are used to define our accuracy statement.
Okay, Mike, we're wrapping up the questions here. We did have one question come in asking about that Minnesota accuracy white paper that Mike mentioned, I think one of the first questions I asked. And they were asking if we could possibly post that out when we post the slides. And we will try to track that down and do that. I'm also going to make a clarification that we will be sending out the slides, the link to the slides, the link to the video of this presentation so you can watch it again or share it with your friends and we will try to include the link to this material and any other reference material that Mike brought up. That will actually happen later this week or early next week. You should get an email from our system mentioning where you can acquire that information. It will not be today, so don't be waiting at your desk till 5 o'clock waiting for it. You'll see it in the next couple of days. So with that, Mike, do you have any closing thoughts?
No, I sure don't.
All right, great. Well, I think that's all the questions that we had. We appreciate you joining us here today. We thank you for coming. Do not forget to fill out the survey, which will appear when you leave the webinar. And one final time, I'll say thank you, and we will talk to you again soon. Thanks, Mike.
All right, see y'all. Thank you again.
Bye-bye now.